Hello and welcome to my first video and also my first video about Jenjin, which is a Kotlin game framework built over libGDX. So I guess this sort of like intro is the framework, and this intro are for people who have experience with Java and libGDX, and obviously writing games in libGDX. The framework is not, it's a 2D framework. It doesn't really overlay the 3D part of libGDX. It's all sort of the 2D stuff. And yeah, that's what Jenjin is really. I guess the first thing I need to say though is that obviously libGDX is awesome. I'm sure everyone who uses it is very thankful to everyone at Bad Logic and who contributes. There's quite a few people who contribute and have created extensions and tools and utilities for it, and it's just a really great community for game development. I guess the cool thing about libGDX is that it is not an engine, it is a framework, and it lets you, so it provides you with the pieces that you need to sort of like compose and build something as you want to build it. So I think a lot of Java developers who use libGDX build their own sort of little libraries and utilities on top of libGDX so that they can do what they want to do quicker. But libGDX, just because it's sort of quite modular and componentized, means you can build what you want. And so I guess that's where something like this breaks away from that. The Jenjin is the thing I've built to help me build games the way I build them quicker. So it sort of like gets rid of a lot of the boilerplate and the sort of usual setup stuff that I'd like to do, and how I instantiate my game objects and that sort of thing. And so I guess if you do start using a framework like this, you lose the one of the big advantages of libGDX, which is flexibility. If you adopt a higher level framework, you lose some of that flexibility. But I've tried to keep it where I can, and I'm trying to make it pluggable. So yeah, this video is just an introduction to Jenjin, which is a Kotlin framework over libGDX. So if you do have experience with libGDX and Java or Kotlin, and you want to write some games, maybe this is for you. I'm looking for feedback. This thing still hasn't been released. It's still a snapshot version, and yeah. So there's an intro and a feedback section. Okay, so let's get into the demo. Right, so what I've got here is essentially a libGDX project, which was generated from the setup app that you can download from the libGDX website. I'm not here to teach you libGDX. I assume you know how to do this stuff. I guess the only difference with sort of the file, the project that would have been generated, is that I have added Jenjin as a dependency to the core project. And as you can see, that is still in snapshot. I haven't released this thing yet. It's still my little toy, but yeah. Anyway, so that's only the only difference really. And of course, this has been Kotlinified. The Gradle project has been Kotlinified, and libGDX has a wiki page to show you how to do that. So, as I said, I'm not here to show you how to do libGDX stuff. But let's have a look at entry point. Entry point is, as you'd expect for a libGDX project, except obviously this is Kotlin. I will not assume, I guess, Kotlin knowledge, so I will, where I remember, I will try and explain any sort of like Kotlin things, Kotlin variations on Java. And I guess while we're here, the first thing we can see is that we've got this thing here, which is a val. So a variable, I guess, is what you would think of it as in Java, but in Kotlin, a val means that it is immutable. Like, I've assigned this thing to this val, I cannot reassign it, that is it. if I did want to start to reassign it, I would call this a var. So vars, variables are variable, and vals are not. But I'm not going to change this, so it is going to remain a val. And then obviously we go into our application listener, but it is not an application listener. It is a JJ game, a Jenjin game, which is an application listener. So that is it really. This is Jenjin's class, and it is an implementation of an application listener, and it has one little entry point, which is where we start running the whole game from. First little bit, I guess, that we're going to do is set up some config. So config, and we are going to set up the world space. So this is really, it's a conscious decision. I'm using Box2D as my physics and space backed thing for tracking coordinates, etc. I mean, I don't see any need in implementing my own stuff for that. I think Box2D is great for it. Even if you aren't simulating physics, you just want to track locations of things, Box2D does that. So locations and positioning is all, and rotations is all backed by Box2D. And Box2D sort of the guidance is that you should think of one unit in world space as being a meter. So one integer is a meter. And so we will do what is it? Game view dots world box width is going to be 20 meters. Game view put the camera at 0. Let's keep it at 0. These are the defaults, but I'm just being explicit. And let's go back to the launcher. We've got a square 1000 by 1000 pixel screen, and in our game world, we are creating a camera which has a width of 20 meters and a central focus position of 0. And then initially we are also going to just be using the Box2D debug renderer. Sorry, if I occasionally do something that looks like it's Python, it's because I write a lot of Python as well. Alright. Okay, and let's get the game on. So taking a page out of libGDX's book, I've got a global sort of singleton object. Singleton, no need for the word global. JJ dot scenes dot instantiate. Alright, and it takes a scene spec as an argument. Right, so what is a scene spec? A scene spec is it's a tree structure. A scene spec is a scene. A single node is a scene, and a scene spec is a single node. A scene spec is also just the specification of a scene. It's the sort of it's not a runtime component. It's something that gets taken by a factory, and it will produce a runtime instance of the scene. So a scene spec is like a reusable specification. It defines something, and you can create multiple instances of a scene spec. And a scene spec can have children, and those children can have children. So it's a tree structure, a scene graph. If you, it's not a new concept in game engines and game building. And each scene spec / node has sort of 3 major paradigms or aspects to it. The first aspect is its physics, and that's a lot of Box2D stuff. The second aspect is its rendering. So any sort of like visual representations that your scene has. And the third aspect is its behavior, which is built on a component system. So you can attach behavior to any node in your scene graph with a component. Right, and we'll get into each of those bits now. Right, first bit we're going to do is set up some physics. So physics, as I said, the physics is box2D based. And so we're going to do just sort of like the hello world of game engine stuff here, and that is a box. So let's body type static body, and we're going to give it a fixture. The fixture is going to have a shape of rectangle. And it's going to have a width of, let's say, 3f. So it's a shape of 3f, 3f. And that is it. Let's see. That's enough for a hello world of the game engine. Let's run it. And there we go. We have our static box in our game world. First hello world in 31 lines of code, which isn't bad. Okay, so let's just have a look at what we've got here for a second and maybe explain some Kotlin sort of stuff as well. So there's sort of like a pattern that I used straight away with the config, and that was just sort of like saying my config class name and then putting a curly brackets, and suddenly I've got access to the context of the object itself to do settings. And this sort of like builder pattern will be familiar to you if you look at Groovy scripts and Gradle, I think. So I mean, here we have similar pattern, Groovy script and Gradle, and you can do similar stuff with Kotlin. And the way you do that, if we go and have a look at jjconfig, we can have a look at the constructor of this object. The constructor of this object takes what is a lambda in Kotlin, but this would just be a lambda. What this lambda is describing that this function is an extension of the jjconfig object itself. So this function is a jjconfig function, which means that it's got access to the context of an instance of the jjconfig. And what we do in this constructor is we take this lambda and we call it on this instance of jjconfig. And so that is how this function has this context and also modifies this instance of jjconfig. What Kotlin has is, I think it's called infix functions, and that means that if the last argument of your function, or constructor in this case, is a lambda, then instead of passing in the lambda as your last argument to your round braces, you can just open some curly braces and define the body of the lambda that you're passing in. So if we go back and look here, that is what we're doing here. These curly braces are the body of the lambda that is the first and only argument of the constructor of jjconfig. So that's how you're able to build these sort of like builder structures, and with these builder structures you're able to create quite nice little DSLs with these builder patterns. And that's the main sort of like thing that the scene spec does. The scene spec is a set of sort of like nested builder pattern lambda functions, which lets you quite nicely build stuff in here. But that's not to say that you can't do anything programmatic in there. Obviously, this is still code. It's not HTML. So for example, if this is Kotlin range stuff, you can, still do programmatic things in here. So if you want to add multiple fixtures, etc., can still do that. Okay, right. So what to do next? I guess what we've got here is a scene spec, and it has some physics. But I guess we want to make a more complex scene first, just to sort of illustrate a little bit more about scene specs themselves. And so for that, I think we're going to make, I don't know, a floor and some boxes and some balls. Yeah, let's do that. So what we can do in a scene, as I said, it's a tree graph. We can create a node. Let's chuck that box in there. And let's create another node. This time, should we make it a dynamic body? Yeah. And we will make it a circle. And we'll keep it sort of similar size, radius of 1.5. Yeah, good. And should we make a floor? We can copy this box, yeah. Static body, let's make the width. We've got a world of 20, so width there, make that 1. Yeah. But at the moment, all of these nodes, this parent is going to instantiate at 0, 0. This is going to have a position of 0, 0 inside of its parent. This is also going to have a position of 0, 0 inside of its parent, and this is also going to have a position of 0, 0 inside of its parent. We haven't transformed or translated these things, and so to do that, we need to use parents. So in that we can go equals, let's -3 dislocate it there, and we can put it, we can keep it at 0. That's our box. Let's put our ball at an offset of 3, and obviously the floor needs to offset on the y-axis, so minus, we've got a world width of 20, so let's do that. So these offsets are relative to the parent, and the parent is at 0, so this will appear at -10. Ooh, that's meant to be a y-axis. I think that should all be right. Let's get rid of this terminal. We don't need that, do we? Yeah. So we've got the box, which is still static, the ball, which is dynamic. It falls on our floor. Let's make this guy dynamic as well. Okay. Putting the Kotlin incremental compiler through its paces here. And so we've got our two little dynamic objects, and they fall on the floor. Right, great. So we can build up these complex scenes with nested things, and the nodes themselves can in turn take nodes. So it's a full, as I said, directed acyclic graph, i.e. a tree. Okay, but what if we want to make more balls and more squares? So we don't want to like be copying and pasting these nodes all over the place to try and make more balls and more squares. Code reuse. So let us define a couple of functions. We will call one ball, and it's going to return a scene spec, obviously. And where's our ball? Well, this is it. and let's make a square. That's our square. So we've got those two functions, and we want our floor, don't we? In fact, yeah, we do. We want a floor because it is a static thing. And let's grab our floor physics body definition here. Okay, so we've got our floor, we've got our square, we've got our ball, and we've got this parent scene which we're instantiating. But we want to reuse these things, so jj.scenes.add scene spec, and we will make add scene spec ball. Ball. Let's add our square. Floor. Yeah. Cool. Alright, so what am I doing here? So, as I said, this is the global singleton, which blatant copy of GDX approach to having a global singleton with all of your various parts of your API. We're using the scenes API, and the first thing we were using from the scenes API was to instantiate a scene. So this creates an instance of this scene in the world. What we're doing here is adding a scene spec to our scenes. So when we do this, we're giving it a path, because these things could be loaded from disk, so potentially, I haven't done that work yet, but that could be sort of like maybe you have an objects file in your storage ball. But if you loaded things from disk, obviously you just give it a directory and would load them all. But for us, we're building this in memory in code, so we are directly shoving a spec into this location in our scenes. And once it's there, it's like a library of available scenes that we have defined, and they're able to be reused. So if we want to instantiate this scene, instead of creating and defining the node explicitly inside of this, we can just go, in fact we want to keep the same params, but we aren't defining this anymore. We're going to just, that was the square, wasn't it? We're going to reuse our square from up there, and similarly for the ball. Instead of defining a node in line, we're going to refer to our library of scene specs. And this is going to be floor. Node reference. Node reference. Okay, so now we have, instead of putting these things explicitly in there, we're using our reusable library of scene specs. So run that. And it's exactly the same as before, but we're using some reusable code. And that means we can make multiple instances of these guys. So let's make another instance of square, and let's put this one at -4 with y of 3, and let's do this ball at 6 with a y of 5. Yep. So now we got more stuff in there. That squares a little bit. Okay, and so these params sort of like define the transforms of your particular instance. What you're doing here is you're creating a new instance of this square, and it is appearing at this x and y location relative to the parent. And what you can do in params is more than just the x and y. You can also play with the rotation. So let's rotate this by 45. Yep. And why not also scale it by, make it half the size. Okay, so still the same square instance. Not instance, but spec. But obviously we've transformed it. We rotated it, moved it around a bit, and scaled it. And yeah. So that is essentially sort of like the physics part and a little bit of the scene spec part. I said there were 3 aspects to scenes, and so we've taken a little dive into sort of the physics part. You can add more fixtures of different types, and you've got access to all of your sort of box2D variables that you'd expect to find in there, so restitution, friction, etc., etc. In fact, should we make the balls bounce, shall we? Let's make them. Let's get a restitution of 0.5, so half its energy is usually in. They're quite bouncy. Let's see. Yeah. Okay, but that is using obviously the box2D renderer. So let's have a look at the second sort of aspect to each scene spec, and that is its render. So what we got here, let's go to the square first. We're in the physics aspect here. Let's open up the render aspect of this guy. And render, it's a similar sort of thing. You can add multiple renders. So this is a square. We're going to add a rectangle. So we're going to add a rectangle render, and it's going to have the same dimensions as the physics, because that just makes sense. Yep. Let's have a look at that. And now we've got some squares which are actually being rendered, not by box2D, but by a render node, and with the default color of white. Again, this is a builder pattern. We can open this up and define the color. So let's see, color. Let's make it like fabric red. Some red fabric bricks. There we go. And let's add some render to everything. So the floor, I think obviously that should be green. And what should this oval be? Bink. Okay. And while we're doing color, let's get the background blue. Disgusting, but you get the idea. Okay, so our scenes have a bit of physics, they've got a bit of rendering. In fact, we can switch off the debug renderer now, because we've given everything a render aspect. The final little aspect is the behavior aspect, and as I said, that's built on a component system. So if you want to define a little bit of behavior, you implement a new component, and there are a few sort of out-of-the-box components for common use cases, but for the purpose of this demo, going to quickly just define our own components. So new class, we're going to call it impulse component, because that's what it's going to do. It extends this component, which is, there we go, construct an invocation. Right, now a component is sort of like your little module for defining behavior, and it's aware of the scene that it gets attached to. So this little class is a runtime as well as sort of specification time class. You can define it here and then attach it to your specifications, and then copies of that component will be made and attached to the runtime instances of the scenes. So components share the lifetime of a scene, the life cycle of a scene, sorry. And so let's have a look at what they are. The one we're looking for is, you've got on add to scene and add to world, and remove from scene, remove from world, and there's pooling involved, but we can talk about that later. The one I want to look at is on add to world. So on add to world, we're going to do some stuff. As soon as this, any instance with this component is added to the world, this action will take place. You can also hook into sort of like the update. So this is a function that would be called on every cycle of the game loop, but we're not hooking into that right now. For this we're going to just get me, which is a function for grabbing this component's scene. Physics root box2d body dot apply a linear impulse. So this is box2d body. We're going to apply a linear impulse to the body, and we're going to apply, just keep it sort of like a unit vector off to 45 degrees. And let's scale it. Oh, not that. Vector 2. Yeah. Okay, we're going to scale it by what? 100. And we're going to apply it to sort of just the center of the object. Yeah, and we're going to, I think it's keep alive. True. Okay, so I mean, it's a very simple little piece of behavior. It's a component which is called impulse component, and all it does is, as soon as the scene is added to the world, it applies an impulse to it. Obviously, you can get much more complex behavior than that. So which should we add this to? Let's add it to our squares. So we add a component. You can add many components, as many as you want. Impulse component. Yep. And so let's have a look at what happens when we start our game. Our squares fly off at 45 degrees. They've got a little bit of behavior. And they're sliding around. They don't have much friction. And so that's it. That is the sort of like very brief intro to Jenjin. My aims were to sort of like get rid of as much boilerplate as I could. Just build a lot of the stuff is a lot of building games is quite declarative. Sort of you build your scenes and your objects and things, and it's all just about saying how much they weigh, where they are, what they look like, and then obviously defining behavior. And that's all like my aim was to just sort of get a nice little Kotlin framework where I could declaratively describe what I wanted my scenes to look like, reuse them and modify them in terms of scale as easily as possible, and really just get down to the business of defining behavior. There's also ways of hooking into like collision events, adding sounds. There's a few things I can show you over the next in further videos. But for now, this was just a little introduction to just get a little bit of a feel for what the framework looks like. And I mean, in 100 lines, we've got, it's not obviously a game, but it's, you know, it's something, and not many lines of code, and it just sort of strips away the boilerplate. In fact, maybe before I go, I can quickly just show a glimpse of sort of the other things that the engine's, well, it's not an engine, the framework built over libGDX. I mean, obviously, the majority of work has been done by the libGDX guys. This is just a layer of abstraction on top of it. But let's have a look at some demos that I've got. So, light and touch, very similar to what I just showed you. We're just defining a couple of boxes and box 2D lighting. There we go. We're just adding a little point light to the physics of one of the specs, and if we run that, let's have a look. What's it? It's a touch. Yeah, so using box 2D lighting, and we just got some physics objects in there, obviously, and that was defined in 79 lines of code, the point light, and adding a draggable component, which made one of those squares draggable. And then I guess we can look at spine. Let's look at composite physics. So in this, you can define multiple nodes and start welding and joining them together. Yeah, we've got a composite complex physics scene, creating reusable composite objects. So if we have a look at over there, we've got a swing hammer which defines the hammer anchor, the hammer, and then it sort of welds them together and it puts it in the library. And this is our whole scene, which puts in a couple of hammers, a spinner, a slider, etc. And then finally, I guess one other thing to have a look at is there's a spine plugin. Spine, obviously, you need licensing to use spine, but there is I've got a license, but you can use Jenjin without the license. And if you do have a license, then you can use the spine plugin. So over here, we're just this is all the code it takes to get Spineboy demo in. You can define the starting animation, register handlers for any of the events that are in the animation. And so let's have a look at that. There we go. We've hooked a sound into the event of the footfall as well as output. There we go. On event and step. Yeah. And I guess also something pretty cool is let's just uncomment those. It will also, if you want to add this skeleton, you can add a skeleton here, and that will build physics for each of the bones in the spine skeleton. So let's have a look at that. Got Spine Boy, and he gets smacked by the hammer, and there's instant ragdoll of his skeleton. So yeah, that's quite a nice little feature. Again, obviously the hard work is done by the people at libGDX and the people who built Spine. But yeah, as I said, this is just a demo of something which is still very much work in progress, and so yeah, if some feedback would be appreciated. If you like what you saw or had some suggestions, I'm open to anything, and yeah, maybe see you in the next video. Thanks for watching.